Okay, welcome everybody to our EOL seminar Tuesday afternoon. It's my pleasure to welcome Tanu Malik from DePaul University in Chicago. She's an assistant professor at the School of Computing and College of Computing and Digital Media since last year.
Yes.
Yep. Her research is in areas of database systems, focusing on challenges in big data analytics, metadata management. Her current research is focused on data provenance, and so I hope you tell us more about that. I didn't know what that term exactly means. Design of scientific data spaces and evaluation of systems for data-intensive computing. Tanu has worked with astronomers, chemical engineers, geoscientists, cosmologists, now with us here. In fact, she has had some contacts with a couple of us here in the audience, at least, in the past, so she's not completely unknown here. Tanu has a bachelor in civil engineering from the Indian Institute of Technology from Kanpur, India, and a master's and a PhD in computer sciences from the Johns Hopkins University in Baltimore. After a PhD in 2008, she worked for a couple of years at the Cyber Center at Purdue University and then moved to Chicago, where she's been at research associate scientist and a fellow at the Computation Institute at the University of Chicago, and a joint appointment with the Argonne National Laboratory. And since last year, she's an assistant professor at DePaul University. And with that, I pass it on to you, Tanu Malik, GeoTrust, improving sharing and reproducibility in geoscience applications. Please.
Thank you, Holger. Thank you very much. And thank you, Kate and Holger, for having me over here, inviting me. It's my utmost pleasure to come over here and present. So what I'll be presenting is GeoTrust, improving sharing and reproducibility of geoscience applications. So GeoTrust is an EarthCube project, and a couple of you, or more than some people, know what EarthCube is. For those who don't, it's a NSF initiative between the Geoscience Directorate and the OCI Directorate. It started in 2011, and I have been with the EarthCube initiative since 2011. Amongst its sort of agenda is to address three things. One is interoperability between geoscience subdomains, find standards for them, and then invest more in advanced technologies for integrating, visualizing, and analyzing data. And the last one is democratize and improve access to data. And that's where GeoTrust comes in, to improve the democratization of the scientific process. Tell you a little bit about GeoTrust. It's a 2-year NSF EarthCube funded project, which was funded last year, starting in sometime in October. Actually, September is what it states, but we got the monies in October. It's a capability project to help build a geoscience cyber infrastructure across 3 geoscience domains right now: hydrology, space science, and solid earth. And it involves 7 institutions as of now: DePaul University, Stanford Research Institute, University of Chicago, Memphis, Colorado Boulder, Utah State, and Virginia. And here is the team for them. You can spot Scott over here, who's from Boulder, and he's a co-PI on our team. And we have Ian Foster, who's known in cyber infrastructure and is part of the Globus. David, and John, who are hydrologists at Utah and Virginia State. Unsu, who's in solid earth at Memphis, and then Asti and Todd, for whom I don't have very good pictures, are in the space science domain. And so all of us have one kind of shared goal, which is improve the state of reproducibility in geosciences. So what I'm going to sort of tell you are tools that we are building that can actually help improve the state of reproducibility. And what is the current state? So what is it? Where are we going from now to with this monies? Where are we planning to go? The other goal that GeoTrust is having is make it part of national cyber infrastructures, as we're realizing that a lot of geoscientists are using data facilities which either NSF is funding or using cyber infrastructure which is coming from the Software Institute's program at NSF. So how can we make it more integrable with those cyber infrastructure, because then it goes across wide community of scientists. So here we have two examples, which is Globus and IRODS, and I'm going to explain a little bit more. We are having HydroShare and InGeo, which are EarthCube projects, and then integrate more with EarthCube. And then the third goal is to advance the research in computational reproducibility. So with that goals, I'm going to sort of as you've heard the words reproducibility quite a bit of time, what is reproducibility, and why do we need it? I'm sure all of us have anecdotes and experiences where you have realized that why is reproducibility important. I'm going to give you my own perspective of where I'm coming from with respect to reproducibility, and what part of the reproducibility challenge, which is itself is very big, are we addressing through the GeoTrust project. And in fact, when I was making this presentation in the morning, this is what I read in the New York Times. It was main headlines, was data manipulated in a widely cited 2015 climate study. And there is a huge debate which is presented as part of this article, is the reason. I mean, I didn't need to go further to look for reasons for scientific reproducibility. But let me give me my perspective. So as scientists, we have sort of come to believe in this self-correcting method. And the self-correcting method is that as scientists, we are doing our data collection, research, and analysis. We go about publishing papers which are reviewed by our co-authors, by our peers, and then publish the paper which generates the impact. And essentially, we believe that if there is something erroneous in our this particular phase, then it will be caught either over here or it will be caught over here, that a badly done scientific method is not published or will not gather enough impact. And we truly believe in this cycle. What we also know as we practice more and more science is that this cycle is broken, right? Reviewing is done very fast, right? And there are ways of getting impact. So as the cycle becomes broken, the scientific publishing doesn't remain self-correcting. And so the best way to fight, if you have actually done your work correctly, is to make your entire authoring connected with data collection, research, and analysis to prove that you have done the correct science, so it doesn't get sort of bogged down with bad reviewing and bad low impact. But even that part is getting very difficult for scientists, and that is the reason for that is that more and more times this part is data computation or software, but what we are publishing is PDF documents, and the two are very disconnected with each other. We have the inputs, which is data or numerical simulations or distributed software and stacks, but our text-based outputs do not connect the two with each other. If they are connected, then the reviewers would have a better way of evaluating what a group of scientists did with their research and make it and actually verify whether the claims made in the paper were right or not. And hopefully the impacts can be gathered by this form of reproducibility. So I mean, so the question is that how can we fix this broken cycle in some senses? How can we actually connect these two things together so that the reviewers get papers which can be verified very easily? Now, to talk about this, there are various tools out there where people would say that, hey, if you want to be reproducible, you have to be open. You have to, first of all, share your code, data, you have to share your environment, and you have to use, you can go start using Dropbox, start using GitHub, put your software up there so that others can possibly use, connect your papers with all the code data, and I'm not sure if people have heard of Figshare, for instance, which lets you put your code and put your data and connect your paper with that. And there are a bunch of these other tools that you can use to start using, to improve the shareability, as I would say, of your code or your data or design, whatever scientific research that you are doing. Two examples that I am very interested in is Dropbox and GitHub. These examples, so with Dropbox, it has really changed the way we share our data and our code with our collaborators. You immediately put your elements into the files into Dropbox and then share with the URL with others, and people instantly can work collaboratively with each other. With GitHub, you get a lot of social recognition for any particular software that you have developed. It provides version control, so you actually see who is taking up the software, other people who are committing to it. Is it actually getting wide acceptance or not? And a lot of scientists actually use Dropbox and GitHub and think that they are actually being reproducible, and their scientific publishing, in some senses, that reproducibility is sufficient for scientific publishing. So here is a claim that I make, that these tools are necessary. So to be able to be reproducible, first of all, you have to be willing to be shareable, right? So they are necessary. Without shareability, we cannot talk of reproducibility, but they are not sufficient for self-correction of the scientific publishing method. So the claim is that we need both shareability and reproducibility. So we might have tackled the shareability problems through Dropbox and GitHub, but not the reproducibility problem. So let me now talk about how I understand what reproducibility is. So suppose you look at a GitHub repo, which is essentially actually of a student that we have, who's part of our project. She put up this WIC pre-process. So this is a hydrology model, and these are some rules by which you can pre-process the data for the model. WIC is the model over here. If you look at it, the first question that comes in my mind with respect to scientific reproducibility is that if I download this code, will this code work on my machine? Will it actually produce the result which it claims to produce? And actually, if you download this code, it doesn't. does not reproduce the result because it is missing what we call as dependencies. How was this code actually running in her environment? So she shared the code. She did not share the data because these were just pre-processing rules in the pre-processing software. So the idea was that the data would be generated once you feed in the data that you have. But more importantly, she did not submit the environment that which particular compiler was she using. These rules are coded in Fortran and C++. She never mentioned the Fortran compiler that was part of it. So if downloaded, the question is, will it run in my computational environment? And that's what we call in computer science the dependency hell problem. That now you are in a hell. You either contact Buckingham or it's dead end, essentially. And that's what one definition of computational reproducibility is, that can we ensure that when this code is up on GitHub, if I download it, it will actually run. The other problem, or another definition of computational reproducibility, is when I look at the repo, is that if I actually produce the data from running the pre-processing rules, I may get different sort of charts which might be presented in the paper which she has written. And the question is that which version of the data produced this result? So it's as you all know, GitHub is a version control repository. I'll check out the latest one, but when I'm looking at the paper that Buckingham is writing, is her result corresponding to the version of software that is available on the most recent repo? Maybe not. Maybe it is a different version that actually produced this result. So can I actually have this mapping of the final result with the version of data which actually produced this result? So we essentially call this the missing lineage problem, that which data file was producing the data that was used in a given result. And that's part of computational reproducibility. As you see, shareability is not ensuring that. Simply shareability is not ensuring that. And the final thing, which I'm sure is all is running in your mind, is what the heck was I doing when I was writing these pre-processing rules? There was some context, there was some documentation. Maybe I was visiting, or maybe Buckingham was visiting some web pages or running some bash commands, or had some semantic information, which is not present, right? That's sort of documentation that Buckingham had to do with respect to those rules to be able to make it usable for someone else. So every software has some context, and the better it is documented, the more usable it becomes, right? So as you're seeing, the open X movement that is there, where you can share code, you can share data, you can share your design, your algorithm, does not sort of address these aspects of reproducibility, which is saying that, hey, if you are sharing this, can I actually use it for my own purpose? And that's how I define computational reproducibility. To be able to use those things, you need the same environment. You need some form of how was the final output produced, which is lineage, and you need some context information. So how do we make OpenX reproducible? So this is what we have proposed, that if you increase your shareability, you would actually improve your efficiency in reproducibility. So what you're sharing over here is maybe a figure or a data. The more you share your code and data, you're actually improving your efficiency in reproducibility. And then you start sharing your dependencies. Finally, one may say that, hey, why don't I just give you my entire, computer, and you take that and actually reproduce what I have. So the amount of the software that needs to be exchanged for the more complicated problem that exists requires you finally to be sharing the entire computational environment, which is also known as like sharing VMs or virtual machines, to be able to understand or rerun what another person might have done. Now, okay, so if we actually really want something to be reproducible, if we really have to share VMs, what is the best way of being able to share these VMs? So here's a little bit of digression into what is the best way of sharing VMs. Earlier, it was thought that virtualization, which is a method which will take your application and actually have your operating system, could be one method of sharing a VM. And so the idea is that you don't, we are asking about sharing entire compute machines. You're not sharing the hardware. All that you are sharing is just the application and the guest OS. As some of you might have heard is that there is new ways of sharing compute machines, which is that you don't share exactly the guest OS. You, in fact, remove that, but you share what is necessary for your application, the dependencies of it, and that's known as the new word for that is a container. So you share this container, which is much smaller in size than actually sharing a virtual machine, and boom, you go. You have another person's computational environment, which includes the software, data, and all the dependencies. When I often talk about this to my geoscientist friends, they are, what is a container? Yes, obviously, it's very difficult for geoscientists to understand what is a container. In fact, for computer scientists, it might be sufficient to say, hey, you can solve the reproducibility problem to an extent with respect to dependencies by sharing a container, but still the geoscientists have to know what to containerize. What do I put in this container? I have my data, I have my model. Who tells me what to put in this container? How do I set up containers? I don't know. Is there some software available? What is? How do I go about that? And then if you have set it up, if you actually came to that and you're sharing it with another person, how do I go about rerunning with the correct parameters and input files? So even though there are some tools available that can help you share one part of reproducibility, which is the missing dependencies, it still has many issues when it comes to widespread usage with a lot of say with any scientists. And so we started this project, which was an EarthCube eager project, and it's known as Geodata Space, where the idea was that the user be provided with a client. So say you are an author of a computational experiment, and you are running an application A, and you run your application A within within a so-called, let's say you have a client, and what that client would do is would get a bunch of information about your application. So it would get some system files, which is dependencies, it will get your data, it will get your code, it will get your environment, and create what we call as a GeoUnit, which is essentially your self-contained application over here. And it will also get the provenance of how your application ran. So in some senses, the execution run of your application, and this is now so you can add metadata somehow to this container, and this is essentially your self-contained unit, which you can give to someone else, and some reproducibility problem would be solved. So the idea was that this container now goes to machine B, and machine B doesn't know anything about this application, can just simply run it without installing, without configuring, without being bothered about figuring out what is contained within the application. So that was the basic idea that we had proposed in this project about self-contained executable units containing what we say the virtualized application, provenance and versioning, and metadata. Now, I want to sort of stress something about this thing is that scientists don't have to think what should be put over here. They don't go about figuring the source code, parameters, configurations, system files, or data. They just have one command to run for their application, and that command does the collection of all this information for them with respect to this particular application. And so that was the primary innovation that we described, that how using operating systems concepts, you can figure out what particular system files or data is your application looking at. So this is very fine-grained, but I'll actually run a demo to show you. So what we did was created a client which essentially lets a user create these GeoUnits. You have a bunch of commands which are available, such as you can add files to your container. You can annotate with respect to adding keywords. You can create a container which can be shared with others, or you can track provenance of it or transfer to different machines. So just over here, it's available through my GitHub page. So you can annotate your GeoUnit by different keywords. You can annotate files which are there in your GeoUnit. You can track with respect to, so this is an application that the user is running, where they're running a Python program, they are inputting data sets, and the idea is that you'll get the execution trace of your entire program. You can package it. That means you can create a container which is self-contained, and you can rerun it on different environments without bothering about installation, or without figuring out what the environment in the other person's machine was. And then you can have a bunch of services with respect to sharing it with others, publishing it, assigning DOIs, and finally, that's your unit of work, which maybe goes as part of a published paper, and you can attach it to, using, say, sites like Figshare. You can attach it with a published paper and somebody else can then just download and rerun it. So that's what we are. That's the client that we enabled for geoscientists. So here is for a little sort of created a little server for people so that they can browse like something like Figshare, where they can actually look at the various GeoUnits that they have created. And you can browse as you're seeing. You have if many of you work on Linux systems, these words would be very familiar to you. Bin, etc., home, lib. That's your actually Linux container which has been created using our client. That's the self-contained, your application-based OS that you have, where your application files, the source code, and the data, and its entire environment is part of it. And then what we have is that little functionality to be able to edit files and be able to rerun over here the application program that has been contained. So what I've planned is that I'll do a demo after my talk so that you can see how this client works, but go further on presenting that how this computational reproducibility, this form of computational reproducibility, is being taken up by other geoscience domains. So I'm sure many of you have questions as to how much of reproducibility can we address in this particular in this form. So far we have shown with respect to two geoscience real workflows. As I mentioned, variable infiltration capacity is a real geoscience model, and we have and it has as I said, the pre-processing rules is Fortran compiler, C compiler, done out of about seven geoscience labs in different universities, developed over a period of time. And yet nobody had the code at one single place. Our co-PI, Jonathan Goodall, who took up the task because he wanted to use this model on a different place so the model was actually developed for the Western region, and he wanted to adapt it for the South Carolinas. Their PhD student took about 6 months to actually figure out how this model runs. And then we said that, okay, we will create different Docker containers of the little parts of workflow that we know, and then you can assimilate them together to see the entire workflow in one place. And it was, frankly, a 30-minute job with our client. 30 minutes, it takes 10 minutes to actually run the workflow. Because we are containerizing, it definitely slows up the process, because now we are observing how your system essentially works. So it adds overhead to it. So computational reproducibility does come at an expense of efficiency. So we've done it with space science workflows, and they're not sort of well known as such. They're of individual scientists. We've done it for high energy physics workflows. These are things that are coming out of CERN, Atlas, and CMS. We have sort of publications which show that our tool is independent of the programming language that you use. So whether you're using R, you're using Python, C++, Fortran, if you're using a proprietary language, we cannot solve computational reproducibility as of now for you. There are methods, but they're not to the technology stage to be able to do out of proprietary software systems. But as long as you're using open source software, we can tackle computational reproducibility. So here is actually the WIC. So it's a 2 gigabyte workflow. We create a GeoUnit of 2.2 gigabytes. There is 36 megabytes of provenance, some dependencies, logs, and then when we containerize with respect, to a Docker container, it adds a little bit of further overhead. So these are essentially the provenance graphs that are coming out of the WIC workflow. As you can see, they are very messy. The workflow itself is quite messy. And one of the things that we are doing right now is mapping this to what the geoscientists understand. What we are looking at is really at the execution level of your model. The question is that the geoscientist essentially wants it at a much higher level of abstraction. And we are showing that we can actually come to that level of abstraction. If you have questions, feel free to ask me, because there is a lot of information over here and I might be skipping some of it. So there were a few lessons learned based on our sort of use of this mechanism to solve computational reproducibility at the scale of geoscience. One is that what we are creating are static GeoUnits. People are not, when you talk of computational reproducibility, people are not interested in what you have done, but they're able, the thing is that I should be able to rerun it with my data set, or I should be able to rerun it with my particular model. So how do we make that achievable for people? So how can I repeat, reproduce, and repurpose the GeoUnits? Our sort of, we were relying a little bit on the national cyber infrastructure, for instance, Globus over here, so that many number of people can use. We were using their authentication mechanisms to be able to store what was being run by people, or be able to catalog the metadata. And so many of the geoscientists, at NCAR, for instance, you have your own particular file server or places where you are storing your own data, or you're storing your own. So how can we make the infrastructure that we are creating sort of oblivious of the place where data is being stored? So that's one thing that we realized, that we could not sort of rely a whole lot on Globus infrastructure, but make it a little bit more transparent. And the final thing was that, the missing context. As you're seeing that with the container technology, we are solving the dependency problem. With the tracking part, we are solving the lineage problem. Where is this file coming from? Which particular other file? But context was still missing. So we had executable GeoUnits, but they are not human readable. So can we get some context information? But what metadata should be added? How should that metadata be even added? Is there a particular standard we should be using? So here is the EarthCube part that we are trying to understand what should be added. So these were the lessons learned from our previous project. In the new project, we are trying to address these limitations. What we are doing is creating, first of all, the location-independent GeoUnits. So you might have done some work which is a computational experiment which is part of your laptop or is part of your the NCAR compute machine on which you might have run a model or done an experiment. But then the experiment is not contained within one machine. It might be on other machines as well. So how do I find the files which are in other machine, add on to the GeoUnit, the experiment that you are doing at multiple places? So one part is to create these location-independent GeoUnits. And apparently the solution is very simple. What we are doing is we are integrating with Git. So we are all assuming that as scientists, at least with respect to reproducibility, we can ensure that they're using some form of version control system. So the client that we are creating, which will capture dependencies, which will capture the provenance, it will do it along with version control and so it's integrated with your Git system. So you are getting the three forms of metadata, which is provenance, versioning, and dependency all together. And then we are using a Git integrated server so that even though you are using at different machines, as long as you have the client, you're running the program under the context of our client through Git server synchronization mechanism, we will be able to ensure location independence. So you can get the same experiment on different machines, add on to it, track its data, and the server will do the synchronization for you. I'm jumping a lot of the functionality over here and simply sort of saying that these are, but if you want details, please feel free to talk to me after the talk. The other problem which we are sort of addressing through the new project is creating this reproducible infrastructure. So one issue that we have had with respect to GeoUnits that we create is where do we host them? Where can a person go and actually see all three forms of information, provenance and versioning and metadata, in a nice cohesive manner so none of the sites, we can go to GitHub, but GitHub doesn't give all this information. We can go to Docker Hub, and maybe that doesn't give us that information. So where do we store? AWS doesn't give. So where should we be storing? And actually, the data facilities themselves don't have a solution for that. So here we are. One of the Geoscience projects, which is HydroShare, has some functionality to be able to store this GeoUnits. It gives mechanisms for users to explore versioning, to explore. We are adding functionality to explore provenance graphs and to host Docker containers themselves. So they have this functionality, and so we are, as part of this, integrating with them. So our GeoUnits could be hosted on HydroShare, where people can see these containers. Further, what we are doing is connecting HydroShare to EarthCube resources, where the container could be taken and actually rerun at EarthCube infrastructure. So you can play with different parameters that might be part of a computational experiment. So this is part of the sort of, in some senses, a use case that we are enabling for some of the hydrology workflows. And we have, as much as my geoscience or hydrology is strong, we have two models which are large scale. We've done for Vic. The snowmelt model use case is another one. But the idea is that we want to take use cases which are either running locally or running in a distributed computational environment, and be able to containerize all, whether it's a local execution or the distributed execution, be able to containerize them, and then be able to host them on HydroShare, and finally rerun on the EarthCube infrastructure. Now, what is the user interested in? This is nice integration. Okay, I would be able to rerun these models, and some of our collaborators are interested in rerunning these models. But what are they looking with respect to computational reproducibility? How do they want to further change these models? How do they want to break them in some sense? Because once you break a model, or once you really add new data sets or find corner cases, that new science is done. And reproducibility is all about enabling new science. So how can we actually enable them to break what is there and create a new use case which doesn't work for a given data set? So we are computer scientists, and our objective is to create mechanisms to be able to do that. And so what we are doing is actually creating an application programming interface, which essentially makes it easy for you to rerun it with different data sets, or be able to change your data set in certain ways, do some stability analysis with respect to different different data sets. And so this is like a little work in progress that you can go ahead and say that your particular container should be tested exactly or partially. So all you have to do is just to rerun this command, and the container either runs exactly or runs from a given particular process in your computational experiment. So it would not run from beginning, it may run from halfway through it. Or be able to do a little perturbation in your test. So that's when we are talking about that you have a range of parameters on which your model is sensitive to. So how can I, if you just say perturb, a range of options for your model would be chosen and then fed into, so that thing would go on in background, and you would finally get the result of your different computational runs. You can change, and you can give the specification. Maybe you want to change a particular equation in your model. You might want to change a parameter. So can we actually change that in the code and then be able to rerun it? And finally, can I validate it at different levels? Is my result being produced exactly like I've had in a previous run? I may supply my result and measure the changes with respect to it. So these are specific sort of layers of abstraction that we are making possible so that reproducibility is easy rather than hard. I would skip this slide, which is a little bit of infrastructure thing that we are doing so that it becomes widely accessible, but go more to the self-describing GeoUnits. That the idea is that with respect to containerization, which is dependency health problem, and the lineage problem, we have mechanisms that can automate this problem for you. But with respect to adding context, we still need human endeavor to be able to document what the experiment consists of. We have curators, but can we make the task easier for curators even with respect to describing the GeoUnits? So what we are doing as part is actually, so we take Baggett right now, which is a mechanism for a standard for describing a variety of files within your within your container. But there are a bunch of standards which exists, and which one is most useful? And here we are essentially resolving. So Scott is the leader for the CSDMS standard names. That there's so many geoscience domains. All of them need the dependency hell problem solved. They want the provenance problem or the lineage problem solved. But when it comes to their particular context, they have their specific vocabularies. They have their specific context as to how they describe the experiment. And many of the things that Scott is leading is essentially in that domain. That for a variety of geoscience domains, are there a few keywords that can be used to describe the models, and as I understand, even the data sets for them. So our thought is that we can maybe give that as part of our client, where when you are doing an annotation for the experiment, you can just use the keywords within this vocabulary, so help you document the experiment faster. And finally, if your GeoUnit is actually becoming like widely used, suppose you have hosted it somewhere and many people have become interested in your model, it might be that you are actually wanting to document it even further. You want to describe, I don't know which particular, you want a nice way of, like, as you have seen many of the GitHub repos, they would describe the version, they would describe the author, they would describe, when was it created. You may have some like bad comments or good comments, which might be part of, it's a nice documentation that you do. And EarthCube has many efforts. One of this is Ontosoft, depending upon the geoscience domain. Ontosoft is very general, which is a semantic way of describing software. So we are planning to sort of integrate with them so that the GeoUnit that we create can be described through in a very standard way. Finally, like I would sort of, some of us over here belong to EarthCube, sort of say that, how do we see ourselves as helping EarthCube or helping the geoscience domain? So EarthCube itself is coming up with an architecture diagram, which hopefully it will get realized within the next few years. And the idea is that, there's a bunch of infrastructure which has already exists, which is marked in yellow over here, or which is coming through other geoscience directorates, like data facilities or the cyber tools, and there's a bunch which is happening in the library sciences domain, which is over here. And EarthCube itself is creating a lot of infrastructure, which is essentially collecting components together of various geoscience data products as well as geoscience models. You can have verification systems. You can have a scientist's workbench where a scientist is doing their work. That's the compute machine, according to me. That's where the science is happening. What we see ourselves is that we are right at the scientist. Our client is right. It will work on your Linux computer. It will work on your Mac OS X computer, where you can just run your application within the client, and boom, you'll have the container, which can then be distributed in many ways through EarthCube channels. So what we are doing right now is actually creating all these GeoUnits in various communities to show that computational reproducibility to a certain extent can be solved, and then be able to rerun it through the eSite infrastructure, which is part of the computational infrastructure that EarthCube provides for us to be able to rerun experiments. Well, this is it with respect to the talk that I have. I don't know if I have time, but what I wanted to do was actually come over here, and I can't see. Okay. Nothing comes. We had this before, we checked it, and person is absent.
Move it way over.
Okay. But then I think it's the display is not mirrored. Let me. Yeah, but then I won't be able to type. So. Display. Let me see if I can. Okay. There. Okay. So, so here I am at one of my client machines, and as you can see, this is some of the workflow that has been shared with us with respect to the WIC processing pipeline. Now, I'm doing a very small demo. In this particular workflow, let me actually open the file. So what the user is doing is, they are running some Python scripts, which is extracting data for soil moisture or averaging it and then plotting it and actually uploading output to S3 bucket. This is a very small workflow, and this is just purely for demo purposes. It runs in seconds. But as I mentioned, the real WIC processing workflow runs for 10 minutes. As I mentioned with our client, and it's based on C++, Fortran, every language that you can think of. And we've been able to containerize with our client. So here you run with our client, and you can see the various commands that are part of the client, and then you start with this GeoUnit, which is essentially saying that here, this is the work that I'm starting. This is the start of my computational experiment, which I would finally like to containerize. Okay, so so I can say ncar demo. So you would say GeoUnit start ncar demo. Okay, and so you would have your GeoUnit start, and then you can go about annotating your ncar demo with any of the key values that you have. We can go ahead and even take data from a file. For instance, if you have stored key value pairs in an Excel sheet or in a file, you can say I am the author. Okay, so so this particular annotation would be added. We can add files. So through an add member command to my GeoUnit, and I think the way to do it is, if I want to, for instance, I have a PDF file over here, and maybe that's the paper that I am wanting to add. So I can go ahead and so this is just adding files or adding metadata, which is context, to your files. And it adds, and I don't know why since morning it is giving me this particular error. Maybe this is something that my student has actually updated, and okay. But the number shows that we have added our file. But more importantly, what you can do is take your program and run, actually track your program. And what this does is it will run your program and create, so this is the script that is running. And at this point, it is tracking the provenance of your program. So this script is, as I showed you, is consisting of multiple Python programs which are reading the data sets, and we are keeping a track between, as I'll just show you, the data set, which particular Python program read it, and what particular data files it wrote out. And then you can go ahead and say package. So this is where, so this is essentially lineage tracking that we have done over here. I ran a program, I captured the linkages between the Python programs and the data files that it had. What I now want to do is take all my Python programs and files together into a container. And that's when we say package, okay? And here, there are multiple commands that you can use. You can list all the packages, for instance, that you have. And we have multiple packages. But more importantly, you can create a package. So over here, I can say level, and level so I say level equals individual, which essentially means that I am containerizing this for myself. I am not containerizing it for someone else. If I'm containerizing for someone else, I would like to standardize my container in certain ways. Here, the idea would be that I create just the app, sort of, the application with its necessary dependencies. It will not have any provenance attached to it, because provenance is probably needed for someone else. It will not be standardized. That means if the other person actually has a Mac OS X computer, this particular container would not run. If you really want to run it on some others, you don't know what environment they would have. They may have Linux, they may have Mac OS X, they may have Windows. I don't know. Then you would like to standardize your container more. But here the idea is that I'm just containerizing this for myself. That means in future, I want to run it on my on a similar system that I have over here, which is Linux right now. So I was doubtful of this, that equals is not needed. So here the entire package ran again, and what it gave me is my self-contained package. And now if I really want to share it with someone else, then I can say package equals collaboration and actually give this particular hash, which would now create a Docker container out of my package, which can then be shared, and it could be run on any other compute machine. What I can do is say package transfer. In fact, no, sorry. So I can say transfer, and at this case, at this point, I can take my package, and there's a little bit of sort of knowledge required, which all sort of systems you can transfer it, different compute machines, different servers, and over here we are transferring to our particular server. And so here this is a reliable transfer that we do. As you're seeing that it is saying that the server destination is this particular sort of machine, and this is the transfer ID. So since we are doing a reliable transfer, we are using some services that helps us do a reliable transfer. and Globus is one of those services. So if you actually look at, so I just now, a few seconds ago, did a transfer to my particular server. So this is my server actually over here. This is my server machine. And I would just log in quickly over here. So as you see, this machine is different. It has different files, different, it's an entirely different thing. And I can run my same client over here, okay? And I can say now my GeoUnit start, and I can, I may remember my work, which was NCAR demo, okay? And I come to over here, and so my package is already over here, and I can do server test, which is essentially now running this package over here, okay? And this is what the Docker container is essentially running. So another person is able to rerun your Docker containers and actually verify. Now, you still have to see whether the data was same or not, and that's part of what we are trying to do. That we will give you more information with respect to whether this experiment produced exactly the same data that you had over here, which you put on the server. Did it have a different data? Do you want to actually go and change this server test in certain ways? And that's where the API that I just spoke about comes in. You can fill in different parameters. Now, I know many of you would be that, we are done with command lines, and, everything is UI based these days. And as I mentioned, we have a little server which essentially, lets you see your GeoUnit, which I just now created over here. You can see the tags that I added, that I am the author, or notes in which I put. We can go about and actually share with other, these are other, we are using a sort of, authentication layer which lets you share with other people who are part of Globus. So these are all the Globus users, and hopefully they will all be HydroShare users with whom you can use. And you can give them read or write permissions. This is the files that we added. If you remember, we added the PDF file, and this is the Docker container that I was, or the package that I had just created, the ED1837 over here. What we have, which is essentially not working, but or it was working before, but is right now, you can browse packages and you can run through command line. And somehow, since today, something my student has done, and it's not working. But the idea is that we don't want to be the one who has this online interface. It is either, we are either going to like right now we are collaborating with HydroShare, who will be hosting our GeoUnits, so that you can do things online, like through web interfaces. Rather than we developing the web interface. I am very bad at HTML and JavaScript, so I don't want to be doing that. That's pretty much it with respect to what we can do. Yeah, I know I'm handling the tip of the iceberg, but I'm sure I'm open for questions.
So you said one of your goals was so that reviewers could be able to reproduce what was going on. So do you have a target for how much time it would take for a reviewer to actually rerun a result? I mean, if it took me 40 hours of running Spectra on my data, I don't want the reviewer to have to wait 40 hours.
So reviewing is a multi-level process, right? In which the idea is that can I run the person's figure, or can I recreate the figures that were there in the paper? I mean, there might be other claims, and we are not solving any of the problems, but with respect to figures, if the user has shared all the experiments through the container, that should be really fast. It should be basically as long as the user created, like it will take the time that the user ran to create the figures plus some extra. And we have done this experiment in my community, which is the database community, which now requires that with the paper you have to submit a computational experiment. They are not using containers right now. It's a nightmare to actually rerun for the reviewers the experiments which are there in the paper. But it is happening. We are stating that with using this technology, you will be able to rerun it much faster. So I can't say, it depends upon what your experiment, how long your experiment ran, which created the figure. That could be 10 minutes of work, that could be 20 minutes of work. You don't have to bother about reinstalling the entire computational, the data and the code. That time would be cut, definitely. Yeah.
Any other questions?
So you had mentioned earlier that there was an overhead associated with the container.
Right.
And I wanted to drill into that a little bit more because there's sort of two places I can imagine overhead. There's an overhead sort of in terms of watching what's happening.
Right.
To create the whole thing.
Right.
But then once you've done that, maybe stored some of that off, it seems like you can containerize it in a way that would still run as fast as it did before, except for whatever the virtual environment slowdown is. And so I'm wondering, is it possible to, I mean, is it because of the sort of the journaling aspect of it, or is it because of the container, the virtual machine aspect of it, or can you get rid of one of those?
Yes, we can definitely optimize a little bit further in terms of rerunning the containers, but the observance definitely adds overhead. So with respect to rerunning, we can take the code and the data that was there and actually remove some levels of indirection, bring it back into the native environment and rerun over there, which would reduce some amount of.
That's what I'm getting at, is if
yes.
the observance obviously takes more time, but once you've observed it, if you can store what you observed, then you should be able to repackage it with the observance turned off and still have it be as fast as possible, right?
True. It's not right now inbuilt in, but yes, we are working on that.
And then let's see, I had another question that had to do with, with persistent URLs, we strive for like 20 years out or something. We try to say, put stuff in a persistent URL where we think it's going to, that URL will be around for a long time. How far in the future do you think that Docker containers will be runnable into the future?
Into the future. So, I mean, the rate at which the operating system. So, if see, if you have contained it and now the next level of interface for the Docker container is what is known as the hypervisor, okay, which is essentially an emulator for your hardware, okay. So if your hardware is totally new, or the hardwares on which you were working have gone obsolete, and so have the hypervisors which interfaced it, you cannot run the Docker containers after that. So you should have a hypervisor which is somewhat available and can run the Docker container that was.
Is there does that mean maybe there should be an effort to create a library of hypervisors that would be preserved for
Yes.
to run all
Yes.
past operating systems
Yes.
or something
yes.
like that?
And that is actually in some ways is being done by companies like VMware and it's not that that's not being done. It is being done by companies like VMware.
Star Trek base, you know.
Yeah. Exactly.
Is that correct? There's a hypervisor that runs the container? There are hypervisors for virtual machines, but the containers are not virtual machines.
The containers are not virtual machines, so it would be a compatible layer. Yeah, exactly.
It's the kernel interface
kernel,
there, right?
exactly, yes.
And so why depend on a binary interface at all when you can, all you really need to preserve is the instructions for building the package, right? And that's how lots of the provenance is going as far as, Vagrant and
may I repeat your question
even Docker.
again,
Yeah.
please? So you're saying that why preserve the binaries even, or so dependencies you mean to say, when
when you can preserve the instructions for rebuilding the package, like Docker and Vagrant nowadays have tools for building up the entire image of the container or the virtual machine without.
But if I have my application, they will still not tell me what dependencies does my application depend upon. So can I figure out the minimal set of dependencies that my application depends upon and put that as part of the Docker container? The Docker doesn't tell me anything of that sort. If I started writing my experiment from the very start in a Docker container, then it is all containerized. But if I have an application which was outside my Docker container and now needs to be put in Docker container so that it could be run at different locations, who's going to tell me what all dependencies does this particular program have? Either I remember it or it is automatically done for me. And it's not only dependencies, it's the environment, like what commands are you giving? Did you set up your environment with respect to certain directives? The directives that you have in your source code, the pragma directives. Nobody tells me all that. And so when you start rerunning it, you're missing environment, the configuration, the dependencies. So you're missing all that information, and then it doesn't run. I hope I'm making it clear that nobody will tell me for a program which is outside the Docker container what its dependencies are. Either the author has to tell or, yeah.
So sort of related, do you make a point of storing the source code in the container and,
yes.
And rebuilding it?
Rebuilding it, yes.
So really, reviewing isn't just a matter of being able to rerun the software. Someone has to inspect the code, right? Is there work being done
right now we are not storing, say, MD5 hashes with respect to the code, but if need be, we can do that. It's just that it will slow the process with respect to building the container, because now we are computing MD5 hashes on the code to see whether the code itself has been tampered or not. Is the compilation exactly the same, or producing exactly the same result as it was producing in someone else's? So we are not doing that just for efficiency reasons, but nothing prevents us from doing it.
Right, but even if you had checksums of the code, you'd want checksums of code that someone else has audited and verified,
right.
Someone independent of the original author. And that's kind of a fundamental problem even for us, right? Observational data, once we publish it, well, who verifies that it's actually accurate? We could put whatever we want in a container and it will generate the results we want to generate.
Right.
But so no one can verify that the software or the data itself was originally intact.
Right. So you're saying that someone else came and tampered the algorithm, which was...
I said I tampered with it before I published it, right? That's the... Right, exactly. Which is why I'm wondering if seems like there's a necessary step of, okay, this version of code that you're running, this other person has verified and audited, and that's the version you should use. And there is a way to maintain this independent
Yes.
view of integrity of the data and the.
So the idea is that you are yeah. Yes.
That's a much more involved.
Yes.
Simple one. Which is where you see DOIs fitting in. So someone's published a paper and now you want to refer to this container
Right.
and everything inside it. And
So
where would that DOI point to?
Yeah, it would point to the container. It would, so you'll, instead of assigning DOI being a data set, so in fact there is some recent research which, so DOI is essentially the way DOIs were designed was assigning them to a single file or a single data set directory which is having multiple data sets. But as you're looking, a container itself is composed of multiple things. So do you keep assigning DOIs to everything which is inside it? Or do you assign a DOI which is to a container and that consists of, it in some senses resolves to different variations of that particular DOI itself. So there is a recent paper which talks about how these DOIs should be assigned, and that should be the one that we should be using. Yeah, I mean it's still an evolving topic as to how to assign DOIs, but as I see, it should be assigned to a container.
Okay, well, let's thank Tanu one last time.
Thank you.